Welcome back, everybody. So we have our exam on Thursday, so literally it's just on 3 sections. So it's going to be probably a little bit of a shorter exam. So exam 2. All right, so next exam 4 covers 4.2, 4.3, and 4.5 only. Those are the only sections. That's it. 4.2 was on the fundamental counting principle and permutations and combinations. Fundamental counting principle. Permutations and combinations. Bring a calculator. I will provide the formulas, the NPR formula and NCR formula, but remember that's a very, very annoying way to calculate it when our calculator can do it like that. So please make sure, because like I guarantee you there's going to be at least 1 or 2 of those on the exam. I don't think that's any surprise. So there's not too many things that we can go over. So there's probably going to be at least 1 or 2 permutations and combinations. So please make sure you are comfortable with how you enter it into your calculator. That being said, I'm willing to help you out and show you where the button is, if you can't remember. So that was 4.2 in a nutshell. 4.3 was on probability. And then odds in favor / against. And then 4.5 was expected value. And then fair price. So the good news was that fair price is directly related to expected value, and then probability or odds in favor or against was directly related to probability. So it's really just 4 topics. So hopefully this one's nice and neat. I said it before the recording started. I'm sorry I don't have a worksheet prepared for today. Just things have been difficult, to say the least. So if you're struggling as well, know that I understand. And so I'm hoping this will be a nice, neat, and easy one. But I'm willing to go over any of these topics, any and all of them if we want to. There's plenty of things to do. Someone mentioned it before classes started. There was a problem in the notes or in the homework that had to do with life expectancy and insurance policies and stuff like that, or investments. You don't need to worry about that. I'll make sure I go through and give people credit for that problem on the quiz and the exam, so that you can get nobody has to worry about getting and if you got it right, I'll give you an extra point or 2. I'll just double count the problem. So I'll go through that later today. Just because we didn't go over that, and it's not too hard to do, but it won't be tested upon. You don't need to worry about that. I will stick to expected values being purely game concepts. So there's a spinner, figure out the expected value of the game, or there's a card game that you have to play, you got the expected value, or there's a game with dice or whatever. But it's always going to be that type of a situation if there are any expected value problems for them, which there probably will be. Yes.
On the question where it says how much should they win, is that the same as expected value? Do we do it the same way?
So the problem should say how much are they expected to win, and so i.e. find the expected value. And so I will clarify the problem, saying if it says that kind of weird language, I'll make sure to put in parentheses that is find the expected value. And I will provide the formula is provided. Odds in favor and odds against, that formula is not provided, but it's very, very simpler. It's very simple. Odds in favor, you're saying chances of success to chances of failure. Odds against is just the reversed version. Chances of failure to chances of success. The The probability formula, I can provide, I'll provide it, but really that's one of those ones that's more intuitive than it is an actual formula. And so from there, yeah. Any of these concepts you guys want to go over? I do have one that I want to do. There's a cheeky little jab at my wife. So I'd like to do in a fundamental counting principle problem. That's a little jab at her. Because I'm the one who does the, like, I do the laundry for our households. I've done it since grad school just because I did it with my mom. She hates doing it, so I do it. That being said, I always fold my clothes. I like my shirts and everything, those get folded and put away in a drawer, but she likes to have her clothes hung up on hangers. But she also doesn't like to get rid of clothing. And she's still trying to figure out her style. So there's a bunch of clothing and not enough hangers. So this is a problem. Well, it's not a fundamental counting principle problem. It's a permutation / combination. So let's call her Kayla, because that's not her name, but hopefully you can see that I have capitalized the wrong letter. Kayla has 13 dresses, but can only hang up 10 of them because she never buys enough hangers. How many ways can her dresses be arranged? How many different ways can her dresses be arranged? So as soon as I saw that it was how many ways, we're talking about 4.1 stuff, because 4.2 is talking, or 4.3 is talking about, sorry, I meant to say we're talking about 4.2 stuff. Did I write 4.1? No, 4.2. Probability is how many ways, is what is the probability of this happening? Expected value is what is the expected value. But if we're saying how many ways, we're trying to figure out the total number of things. So if I do this, I'm talking about either a permutation or a combination. Which one would it be? Take a second to think about it. I want to make sure everyone gets a chance to think. Permutation or combination?
Permutation.
Permutation. So as a reminder, permutation, look for the words order / arrange. Combinations, look for the words choice or select. So because with permutations, order matters. Now I know, like, personally, I see this and I feel like order doesn't matter. Like, it doesn't matter if the blue dress is first. Unless you've got like OCD or a little bit of neurodivergence and you have to have them, you got to do this dress first, then this dress, then this dress, and you got to work your way through it. So I don't know if anybody does that. If you do, awesome. If you don't, not a big deal either way. I just choose it randomly, but the fact that it says arranged is telling us that this is a permutation problem. Because it says arranged, we're talking that the order does matter. Despite the fact that this problem makes it feel like it doesn't, the fact that it says arranged is talking about, or like this problem could also be reworded saying how many ways can her dresses be ordered? And as soon as you see that word order or arrange, it's talking about a permutation. So it's 13 total dresses chosen 10 different ways. 13p10. And you can calculate that by hand if you really want to using the formula, because I will provide it, but it would be much better to just plug it into your calculator. 13 p10, and you get 10378368000. So that's
1 billion.
1 billion different ways for her dresses to be organized. So, oh, a fun follow-up question is how many years? Oh, that would be a really cool question. Is how many weeks can she do uniquely? How many weeks can she uniquely do a week? Like if she does red, white, blue, like red, white, blue, green, like red, white, blue, green, yellow, orange, that's 5, 4, 5, 6, and then pink. Like that is a unique week. And then you could also do pink, red, white, blue, all that stuff. How many different weeks will that take care of? That'd be a fun question. So, but apparently, as long as you have 13 dresses and you can only hang up 10 of them, you have 1 billion choices. No, like, and that's selling the 37 million short. 37 million is a lot of number, is a lot as well. But a billion. Well, like, and hopefully, like one thing I want to remind us of this is just to make us angry at our capitalistic overlords. $1 billion is a lot of money. Nobody needs $1 billion. So just so we're clear, be angry that there are people that have $1 billion in this world. There's many different ways that you can see it. I'm sure you've probably heard them, but like the fact is, $1 billion, if you like to, the amount of time it would take you to get $1 billion is insane. No person should have that much money. Anywho, sorry, get off my soapbox. But anywho, that's an example of a permutation. We could do another one. This one, example. Every day in Mr. Kellertinian. Oh wait, no. Well, let's do the. What was her name? What was her name?
Hey.
My APUS teacher, my APUS history teacher's name. Miss Troyan. Every day in Miss Troyan's class, 5 students are picked to clean up. If the class has 27 students, how many ways can this occur? How many? This occur? I miss Miss Troy. Her class gave me an ulcer, but there were 4 APUS US history teachers at my school. There was one who was basically guaranteed to always give a quiz every week. Like that was just his MO. There was another one who very rarely gave them. There were 2 that were very rarely gave them, and then my teacher, Miss Troyan, she was a wild card, and so every day you had to wonder if you were going to have a quiz, because sometimes we had a quiz every day of the week. Other weeks we had no quizzes. So the anxiety started to get to me. But she was a great teacher. Anyways, so is this a combination problem or a permutation problem? So there is a word in there that directly tells you what it should be, but it's not easily found. It's the word pick. So the word picked does tell you that this is going to be a combination problem, but it's better to, like, you always want to ask yourself, like ideally look for that word first, but if you can't, then ask yourself, does order truly matter? And I will make sure that the problems that where order does matter, and it's not very, very clear like the previous one, that I use the keywords like arranged or ordered or chosen or picked. But this one, does order matter? Does it matter if I get told, if I get chosen first? We have no different positions. It's not like I'm going to have to clean the desks and someone's going to have to clean up the floors. We're all going to work together. So it doesn't matter if I'm picked first or last. That group of 5 kids is going to still just be chosen at random. So that's going to be 27C5. Does that make sense why this is a combination problem? I can explain it again if you need. So 27C5, that is 80,730. So the bigger number always goes first, because because the way permutations and combinations works, it's n things chosen r at a time. So the n things chosen is how many of your pool, and the another number is the subset that you're using.
There's a very easy way to figure it out. If you put the smaller number first,
Oh,
it'll give you an error and you can't
Okay, yeah, I think I
capture
tried that too, just to see.
that is true. That is another way to figure it out. Is that it cannot be done otherwise. So the bigger number always comes first. That being said, just as a fun little tidbit, what do you think -1 factorial is? What do you think -1 factorial is? There's a lot of different questions. It's a fascinating thing. What about 1/2 factorial? What would 1/2 factorial even mean? And I'll tell you, you can't compute it by hand, but there is a function called the gamma function. So that's a capital gamma. There's a thing called the gamma function and the beta function, and they're fascinating. They involve a lot of high-level mathematics, and it just so happens what's magical is that the gamma of n is equal to n minus 1 factorial, which is wonky as hell that this function ends up giving you factorials for integer numbers. And then somebody figured out how to find gamma of 1/2, or of 3/2, I think. It ends up being something nice. And that allowed us to find factorials for non-integer numbers, which was wonky as all get out. Very cool function. It'll be on the exam. No, I'm kidding. There will be an extra credit problem on the final quiz, just to let you guys know. It will be approachable, hopefully. Not going to be too crazy, but it'll be a way to boost, or maybe if it's on the quiz, then it doesn't benefit us as much. So there'll be an extra credit problem on this exam. There'll be an extra credit problem on this exam. And so I hope you guys enjoy it. I've been trying to train you guys for it this entire time. Hint, hint, wink, wink. But anyways, I'm getting sidetracked. Any other questions on this? All right. Fundamental counting principle problem. Example. A password for a secret base is made up of 3 numbers between 0 and 9 and 3 letters, A to Z. How many passwords are possible with repetition? That word, please be on the lookout for that word. With repetition versus without repetition is important. Because if you allow repetition, then the answer of 000AAA is a possibility. But if you don't allow repetition, you can't do any of those things. So no number can be repeated. So this is a fundamental counting principle problem, because what we have is 6 different events. We have the first letter, the first number, the second number, and the third number. And then the fourth entry, which is the first letter, fifth entry, which is the second letter, and the sixth entry, which is the third letter. And so each letter or each entry has a separate number of outcomes, and we multiply the outcomes together to get the final answer. So how many numbers are between 0 and 9? 10 numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 numbers. I always screw that up. So there's 10 numbers for the first entry, 10 numbers for the second entry, 10 numbers for the third entry. And then how many letters are in there in the alphabet? 26. So 26 each time, 26 times 26 times 26. So let's do that. So 10 times 10 times 10 times 26 times 26 times 26. You get 1,757,6,000. So that's 17,576,000 different ways. So because repetition is possible, they always say 10 and 26. But without repetition, the answer changes. Because now if you use one number, then the next entry you can't use the same number. So it would be 10 for the first entry, but then 9 for the second entry and 8 for the third entry. Because once you've used the first two numbers, you only have 8 numbers left. And then same thing for the letters. Times 26 times 25 times 24. So without repetition, you have to reduce it each time. And there's even more fun questions you can ask here. Maybe the requirement is that the numbers can be repeated, but the letters cannot be. Or the letters cannot be repeated, but the numbers can be. All those types of things. Whatever you want to do, but this one, 10 times 9 times 8 times 26 times 25 times 24, you get 11,232,000. 000. So 11,232,000. So you lose out on about 6 million options in that way. Kind of crazy, like just by not allowing repetition, you lose out on 6 million. It's all like, it just kind of fascinates me when you think about it. You've only reduced this number by 1 and this number by 2 and this number by 1 and this number by 2. So at the end of the day, we've only reduced the numbers by a total of 3 or 6. We've only got rid of 6 letters and 6 numbers, but when you multiply them, that makes such a substantial change. I think that's always cool. So any questions on that? All right. Another example, that's kind of all the topics from unit 4.2. And then we can go to 4.3, which is probability and odds. Let's do some examples of probability, and then we'll do some examples with odds. So example, a single card, or actually I suppose I should open this up. Does anybody have any probability type of problems that they want to go over? Like dice. Oh, and by the way, reminder, I will be putting the 6x6 grid of sums of dice rolls on the exam. I'm not saying that there will be a problem on that, but you don't have to have that memorized and you don't have to recreate it on the exam. They will be provided. So is there any type of probability problems that you guys want to go over? Card. Okay. A single card is drawn from a standard deck. Find the following probabilities. Part A will be the probability of a face card. Part B will be the probability of a even card. Part C will be the probability of a face card, or sorry, a queen or a red card. Let's do those three. So what? An and one, okay. Yes, we can do an and question. Part D, the probability of a red and a 2. So the card is red and it is a 2, not a red and a 2 card being drawn at the same time. Does that make sense? So like, we haven't talked about that type of probability. That's what we call compound probability. And that is something we did not discuss. So what is the probability of like drawing one card and then drawing another card? That changes things. And we haven't talked about that yet. Nor will we, but if you want to know more about probability, even after the semester's over, you can definitely talk to me. So probability of a face card. And I can also, would anybody like me to put the suit, like the breakdown of those things on the exam, on the back sheet, just about the properties of cards? I'll put them on there just in case. So there's 52 cards in the standard deck, 13 of each suit, 4 suits, and 2 reds, 2 blacks. And then the list of each in each card. So I'll make sure it's nice and neatly organized. But so there are 3 face cards in each suit. There's a jack, a queen, and a king. And since it says just a face card, it doesn't say a red face card or a diamond face card or anything like that. It's one of each, like there's 3 cards in each suit, 4 suits. So that's going to be 12 total out of the 52. 3 from each suit, 4 suits, that's 12 face cards total. So the chance of drawing a face card is the number of successes, which there are 12, over the total number of options, which there are 52. Probability of drawing an even card. So there's 2, 4, 6, 8, and 10. There are 5 even cards in each suit. 4 suits, that's going to be 20 total. Part C is arguably the hardest one here because there's a double counting here. So this one I'm going to so red card. There are 26 red cards. So we can either utilize, there was that formula, by the way, that P of A or B is equal to P of A plus P of B minus P of A and B. But you don't have to memorize that. You can just do it by hand. There are 26 red cards. There are 4 queens. But we're going to do, but we'll take away 2. So this will be 26 plus 4 minus 2 to avoid double counting the 2 red queens. And then divide that by 52. Let's take a moment to understand that. So 26 red cards total. The probability of drawing a red card is 26 out of 52. And that is including the 2 red queens. And there are 2 additional queens on top of that. So you could do this in a lot of different ways. You could do 26 plus 2, saying that you've already counted the 2 red queens and the 26 red cards. Or you could do 26 red cards plus 4 queens minus the 2 red queens, because we've already accounted for them in the 26. There's a lot of different ways you can do it, but that ends up being 28 out of 52. Does anybody need me to explain that in a different way or explain that again? Sure, absolutely. Thank you for asking. So there are 26 red cards total in the deck, but that includes 2 red queens. So if we want to draw a queen or a red card, there's 26 options from the reds. There are 4 queens, but there's a double counting that's happening here because there's 2 red queens. So we have to take those into account by subtracting them because we've already accounted for the red queens here and the red queens here. So we're double counting them. So we're going to subtract 2 to counterbalance the double counting. Hypothetically. So if it said an even or an odd card, there are no even and odd cards at the same time. There's no card that's both even and odd at the same time. Or if it said a jack or a queen, that is a situation where they are what we call disjoint, because there's no situation where you can draw a queen and a king or a queen and a jack at the same time. It just so happens that with this situation, you want to count like the thing is you always subtract off the double count. But there are certain circumstances where there aren't any double counting.
So, 26 plus 2.
Yeah, we could also do 26 plus 2. Since you've already counted it, like that is the other way to do things, is to count up all the number of ways that things can occur by hand. So you can either draw 13 different cards in the red suits, including the queens, and then you add on the 2 additional queens that you haven't counted, the queen of spades and the queen of clubs. Either way is fine with me. So probability of red and 2. There is only 2 red suits, and there is only 1 2 in each suit. So this is going to be 2 out of 52. And you don't need to reduce your answer. You don't need to reduce your fractions. Please don't do it on the probability problems.
Wait, why was it 2? Sorry.
Oh, no worries, no worries. I'll explain again. So there are only 2 red 2s. Yeah. That like, yes, there are 26 reds, but there are only 2 of them that are 2s. I guess would have made this problem a little more complicated was red and even. Because then you have to go through all the red even numbers and count them all up. Any questions on those? We can do another example of probability and then we'll talk about odds. Let's do one of my favorites. Example. A gumball machine has 20 yellow, 15 red, 6 green, 12 blue, and someone give me a prime number. 19. Perfect. Good night. Good prime number. 19 white gumballs. Find the probabilities. Part A, be drawing a white gumball. B, drawing a blue or green. And then part C will be drawing a the probability of drawing a yellow after a yellow has already been drawn. we wouldn't have a question C on the quiz or on the exam because question C has to do with compound probability. This is probability that has been put upon additional probability, hence the name compounded probability. But I want us to think about it because I think it'd be a good problem. So, solution. There's a preliminary step that we need to do before we even calculate probability. Because what is probability? It is the number of success, like the number of ways the outcome can successfully occur divided by the total number of outcomes. But we don't know the total number of outcomes yet. How do we find the total outcomes? Add all the numbers together, because if they were all the same amount, if we knew that there was the exact same amount of all the different types of gumballs, if they all had 20, then we wouldn't really need to add them up. We would just take the number and divide so yellow, red, green, blue, and white. That's 5 different colors. So if they all had the same amount, we would just say like the answer would be 1/5 for drawing a white. But because the amount is differing for all of them, we need to take that into account. So we'll add them all together. 20 plus 15 plus 6 plus 12 plus 19 is equal to 20 plus 15 plus 6 plus 12 plus 19. Oh, my calculator was off. 72. 72 total outcomes. So part A, the probability of a W for, I'm just going to use an abbreviation P of W for P of white, probability of white. But you can write P of W of white or whatever you want to do. And that would be 19 total ways for success divided by 72. over 72 different ways. Or 19 and over 72 chance. Part B, the probability of a blue or green. So we just add them both together, and we don't need to worry about any double counting because there's no blue and white gumballs or blue and green gumballs. So we just add them together. There were 12 blue and 6 green. So 12 plus 6 over 72, that's 18 over 72. That's it. So once again, part C will not be tested upon because that's what we call compound probability. But I want us to think about it. We know that one yellow has already been taken. So that for part C, one yellow has been taken. And we're going to assume that the person is not a monster and chewed it up and put it back in there or whatever, or took it out and covered their greased their hands and then put it back in there. We're going to assume that they took it and they ate it. So now there's only 72, or now there's 71 gumballs left. And there's only now 18, or wait, how many yellows were there?
19.
Yeah.
20 original.
19 yellow left. Because one of them was taken. And that's why it's compounded, because the implications of the first change the order of the second. So that would be a probability of 19 over 71. So that is that problem, but definitely assume that that would not show up. It would be more like part A and part B. What is the probability of drawing a white? What is the probability of drawing a blue or green? You can extrapolate this. There's a billion questions you can ask. What is the probability of drawing a blue, a green, or a yellow? Oh, here's a good one as a bonus. The probability that it is not, what color haven't I used yet from the set? Not red. the probability that you draw a not red. So anything but a red. So all we need to do then is just add up all the other gumballs and divide it by the total number. So this would be over 72 because there's still because there's still 72 gumballs. And then we add up 20 yellow plus 6 green plus 12 blue plus 19 white, which is 20 plus 6 plus 12 plus 19. So 57 over 72. Which I suppose we could have just done 72 minus 15. Should be another way to do it. But so the fact is, any other gumball will work. So you could the way you could succeed in this probability, the way the numerator, the number of successes is either drawing a white, a yellow, a green, or a blue. And that'll do it. Any questions on that? Okay, let's do an odds in favor versus odds against problem. We'll do 2 of them. Example. The odds in favor of Phil putting a Paw Patrol question on the exam are 13 to 4. Could be. Could be, you never know. Find the probability that he doesn't put one on. So we really need to parse through the information here because there's this is a very big deductional problem. The odds in favor of Phil putting a Paw Patrol question on the exam are 13 to 4. Find the probability that he doesn't put one on there. So we have to understand what the odds are telling us. 13 to 4 in favor. Write this down. Favor for 13 to 4. That means 13 chances of success to 4 chances of failure. And what and so we have to so that's what it means based on the raw definition. So a 13 to 4 odds in favor means 13 chances of success to 4 chances of failure. What that would mean in this context is that there are 13 chances for me to put on a Paw Patrol question and 4 chances that I don't. So that means that there's a total of 17 total outcomes. The reason why I mention that is because that's what probability is. Remember, the connection here is that probability is number of ways the event can occur divided by the total number of outcomes. So when you're given odds, you need to add them together to get the total number of outcomes. So the question is the answer 13 over 17 or 4 over 17? Take a second. $13 or 4 over 17? 4, yes. So the odd, because it's saying that the chances that what is the probability that I don't put one on the exam? So the numerator, the number of ways that succeeds is if I fail to do it. Does that make sense? So take a long time reading these problems because there's a lot of information to parse through. There's a lot of deductions that need to be made. The fact that it says 13-4 in favor means that there are 13 chances for me to put the Paw Patrol question on, 4 chances that I don't. And so that's a total of 17 outcomes. And since the probability is finding that I don't put one on the exam, that means the numerator should be the 4. Because that's the ways that I don't put one on the exam. Does that make sense? Remember, you can work backwards too. And that's what the next example will be. And saying, let's do an actual scenario. Your first card in blackjack was an ace. Find the odds against you getting 21. So obviously I would explain the rules of blackjack because I don't know if everyone knows them. But to let you know, all face cards are worth 10. And the ace is worth either 1 or 11, depending on what you need. So like if you get a 10 and another 10, and then you draw an ace, you can either think of that at like you could opt to say that I want my ace to count as 11 and lose, or you could say no, I want my ace to count as 1. So aces are worth 11. So what we need to do is we need to draw like the odds, like in order for us to get a 21, we need to draw a face card or a 10. To get 21, we need a face card or a 10. That's how we would get a blackjack. Like, does blackjack, when you say like to get a blackjack, does that mean you have to get a black, like an ace and a black, like in a jack of clubs? Is that the requirement? Okay. So, cool. Perfect.
You get paid double sometimes.
If it's a specific one, like,
No, just long as it's the ace you say.
yeah,
Yeah.
okay.
Long as it's like that.
Gotcha. Like I wasn't sure if there was like a specific requirement, like you know how there's the royal flush is ace or is jack, queen, king, ace.
Right. They do have a game where, if you get 2 queens of black hairs, you get paid for that.
Oh, okay.
If
That's-
you bet that.
That's fun. Gotcha. Learn something new every day. Like I don't gamble enough. Or probably that's probably saying that I do gamble enough. So we need to get a face card or a 10. So what we need to do is we need to find the probability of a face or a 10. So if we can find the probability, then we can find the odds. So the probability of a face or a 10, and it doesn't matter the suit. There are that would be 4 different cards in each suit. Because there's 3 faces plus a 10, that's 4 different cards in each suit. So that's a 16 out of 52 chance. Which would mean 16 successes and 52 minus 16, which is. Yes, go ahead, Jason.
Wouldn't it be 51 because you drew an ace already from the deck?
Ooh, good point. Good point. That's a very good point. 16 out of 51. So let's make a comment there. Because we already drew an ace. So there's only 51 cards left in the set. If this was a question on the exam, by the way, if you wrote 16 out of 52, I'd still give you full credit because that's an implied aspect that we don't necessarily consider when we're thinking about the game. So And it should be 51 failures now. So that's 35 failures. So I feel like this question is becoming more complicated than it was supposed to be. So maybe we'll do another one after this that's actually more straightforward. But because we drew because we drew an ace already, and we're assuming the dealer hasn't drawn his cards yet. His or her cards or their cards. So there would be one less card in the set because an ace has already been drawn. But there's still no face cards or tens have been drawn yet. So there's still four of each of four of those cards in each suit. So there's 16 total ways to get a face or a 10 over the 51 cards because one is already drawn. That means if you were to take that probability and think about it in terms of successes and failures, that means there's 16 ways to win. And then you take the total number of outcomes and subtract off your successes to get your failures. So 35 failures, 35 cards that don't make you win, get a blackjack. So this is saying the odds against. So with the odds against, you put the failures to successes. Favor successes to failures, against failures to odds against failures to successes. So your odds against are 35 to 16. Yes, of course. Odds in favor, you put successes, failures. And then odds against, you write the failures first, and then the successes. It's just one of those things. I don't know why I know why, because there's, if you're a betting person, there's either you want them to win or you want them to lose, like in a sports game. So they both do the same thing.
That's in a comment then. Like,
Oh, is that gonna be provided? Sure, why not? Let's make it, let's be nice. The springtime weather, it's nice. Let's have a fun last exam.
Don't feel like
wait,
spending
so
more.
where did you get all these numbers? I'm so sorry.
Oh, no worries.
That was really confusing.
Sure. So the odds and so where the original stuff is coming from is just from probability on cards.
Mhm.
So there's 52 cards in a deck. Since we drew an ace, there's only 51 cards left.
Mhm.
And then the 16 is coming from the fact that there is 3 face cards in every suit, a jack, a queen, and a king, and then or a 10. So that's 4 total cards in each suit, and there's 4 suits, so 4 times 4 is 16. So that's where the 16 is coming from. The reason why we did 51 minus 16 is to figure out the number of failures, because in order to do odds, you need chances of success and chances of failure. Which one comes first depends on whether it's saying odds in favor or odds against, which will now be provided. So if you want to know the number of failures, you take the total number of outcomes and subtract off the number of successes, because that would tell you all the ways you'd fail. So that's where the 35 is coming from. Now we're saying odds against, so we want the failures first. So that's why it's 35 to 16.
So when you give us like the cards,
Mhm.
what would be the? what would you do?
How about this? This is how it will be presented. It'll say, deck of cards info. What it'll say is there are 4 suits, and it'll say diamond. All right, and I'll do this. I'll do red suits, diamond, and heart, black suits, which are clubs and spades. like that. Sounded aggressive at first, and so I don't know. I like ever since after last semester. I don't know if you guys were around for that. That was
Yeah.
Yeah.
a little creepy. Granted, it wasn't on our campus, but still. But so all right, 4 suits, 13 cards in each suit. And then I'd write ace, 1, 2, to 10, and then jack, queen, king. And then I write that face cards are jack, queen, and king. That's what I'd write. Is that sufficient?
I keep asking for too much, but would you like a picture of like the deck of cards on the screen while taking the test?
I don't see why not. That's
Sorry, I'm
No.
more like a visual learner, so it's like hard for me because when I see all this, I'm like overwhelmed, like I don't understand. So
Gotcha.
like say if like, so when I was doing my homework, I would put like this up to like do it.
okay.
Cause it's just like, oh, okay, I can see there are 1, 2, whatever.
So yeah, like I'll try to make sure it's very, very clear. I'll either put that on the exam itself or I'll put that information on the exam and then also put it on the screen.
Okay.
One of the two. So yeah, it should be clearly presented and this goes for all students. If you need like clarification on any of those things, please feel free to ask. I can answer general questions about, I can't tell you what the probability is, of course, but like if you're saying like, what's a face card or what constitutes this requirement, whatever, I can clarify that. So,
In the home, there was a problem about jokers.
don't worry about that on the exam. There's no joker, like, I am a joker, of course, but, I'm not gonna put any jokers on the exam. So typically there's 2. There's 2 jokers in a deck.
Does
typically
it
speaking.
count?
They're not used for actual like probability because they're not supposed to stay in the deck.
Yeah,
Oh, so they're additional?
yeah, they're additional.
54.
Yeah, so there's like, it would be 54 if the jokers are included, but, yes, and the standard deck is just 52. Yeah, only in certain games. And I don't even like, was that like, that's a history lesson that I don't know, that I'm not privy to. I don't know it. But I don't know why they put jokers in the deck. Does anyone know? Like, I'm sure that's a fascinating bit of information as to why, like, you know how there's 360 degrees in a full revolution, right? Why is it 360? Why isn't it 100? Like that would be a nice round number. Why isn't it? I learned this recently. It's the Babylonians. The Babylonians are the reason why it's 360 because they count in base 12 and 360 work really well because it's 360 divided by is 30. And so they're actually, this is actually the reasoning for it is that the way they counted their days and their yearly calendar, they did a 30-day cycle and 30 times 12 is 360. And they counted in a base 12 system that when they counted, they used the 3 parts of their digit of their finger. So this was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it was really cool. That's how the Babylonians counted. And so the reason why there's 360 degrees is that their system was one of the ones that we thought was the cool, that European countries, when they started to try and formalize it, granted, this was happening everywhere in the world, not just European, but this is the only thing I know about is the European aspects. They were studying ancient civilizations, and when they were figuring out trigonometry and stuff, they ended up deciding that they followed their measurement system. That's why there's 360 days, or 360 degrees.
I think that's a weird too. The jokers had in history, the diamond, the heart, and then it was like some other Tony wedding the heart.
Okay.
It was the spade, the diamond, the heart. I think I want to say an acorn or something. Like when the very first deck card
Cards.
came out.
Gotcha.
I learned that. I learned.
There's always those, there's so many fun little nuances. One thing I always wanted to It's a fun, like, this is a cool little tidbit for you guys to know about hermit crabs. I know this is not math related at all, but this is a fascinating topic that I just learned about recently. So crabs, just like anybody, grow. And what happens when a hermit crab gets too big for its shell? What does it do? It leaves its shell, but that's dangerous, right? Because then it's exposed. So how does it find a bigger shell? Well, this is the nuts thing. They wait in a spot. If they find a shell that's too small or too big, they will wait, and other hermit crabs will line up so they can kind of do a little dance and switch shells. It's like they literally wait for other hermit crabs to get around so they can switch shells and get to a bigger one. It's fascinating. Super cool. They will actually literally wait around and wait for other crabs so they can trade off houses. Super cool. Super cool. And now you know that, and you can't unknow that. So you can bust that out at parties. And anyways, so yes, I will provide that information on the exam, in hopefully and also in a visual way, in some way, shape, or form. Let's do another odds question to actually do it properly, without having to worry about like drawing the ace. I thought it would be a fun problem, and it ended up just being more complicated than it needed to be. Example, a sports website says the probability of the Browns making the playoffs are is 2 out of 1,003. Why? I don't know. It's cool. It's a quirky website. I'm kidding. The Browns, like just the Browns from what I remember. I know they gotten better. Let's be realistic. Let's change that from the Browns to a more reasonable team, aka the Jets. Burn on the Jets. Oh man. It might have been higher if Aaron Rodgers hadn't broken his gotten his, what was it, his Achilles?
Like, yeah, he tore it like in his, like, after 3 snaps.
Yeah, 3 snaps into the first game.
Yeah.
Oh man. So the Jets making the playoffs of this. Find the odds in favor of them making the playoffs. I will try my best to not be super like convoluted in these problems, because like what I could, like this problem could become a really, really mind circle, like just a complicated mess. If I said like find the odds in favor of them not making the playoffs, it's like a bunch of double negatives. So but point being is always take these problems slowly and make sure you identify all the successes to failures. What is a success? What is a failure? What are we looking for at the end of the day? So, solution. The probability of a Jets playoff are 2 over 1,003. So that means that there are 2 successes and 1,003 minus 2, so that's 1,001 failures. You realize there's a lot more failures than that in the Jets. Kidding. Sorry if you're a Jets fan. Not sorry that I'm being mean to you. Sorry that you actually are a Jets fan. Oh man, sports teams are fun to make jokes about. But I know it doesn't make sense in the real world. Like you can't fail twice, but like there are many different ways. Like that's the way the math is stated, is that there will be 2 chances for success, and then because there's a total amount of outcomes of 1,003, that means that the other 1,001 outcomes are failures. Now we wanted the odds in favor, and odds in favor are successes to failures. So the odds in favor are 2 to 1001. And you don't need to you don't have to write all this information down on your exam. If you're able to compute it in your head, like you just know what the numbers are and you write it down, you can still get full credit. I only caution you against that because if you get it wrong, and I can't tell how you got your work, I can't give you any credit. But if you show what the probability is and you write some certain things down, I can give partial credit for that. But it's not, you don't need to write odds in favor or whatever. You can just write 2 to 1001 and call it good. Any questions on that? So that's a much better example of converting probability to odds. Let's just be safe. It is finals week. It's getting towards finals week after all. It's a terrible thing that I have to do, but just anyways. Let's see here. Let's go back to something fun. So we've done probability, we've done 4.2, we've done 4.3. The only thing left is 4.5, which is basically just expected value. So let's do an expected value problem. Example. A game costs, say, $2 to play, where you roll a single D12. In case you don't know, in case, D12 means a 12-sided die, which they do have. In case you play any Dungeons and Dragons, there's a D12. It's a D4, D6, D12, D8, and a D20, typically. If you roll, let's see here. Let's make some interesting choices. If you roll an even number, you lose. Semicolon. If you roll a 1, 3, or a 5, you win $4. And if you roll a 7 or a 9, you win $10. And if you roll an 11, you win $20. Find the EV. So 1, 3, so all the evens are taken care of. So all we need to worry about is 1, 3, 5, 7, 9, and 11. So yeah, that covers everything. A good game will have all cases taken care of. If there's uncharted territory, then that's a problem for the game. But yeah, so that's it. If you feel comfortable just going straight into the formula, go right ahead. The expected value formula, as it's presented, I'll present it this way. It's probability 1 times result 1 plus probability 2 times result 2 plus all the way to last probability times last result. So the way I like to do this is I like to make a chart that says outcome, probability, and then the result. So we just go through it. The outcomes are listed And I'll probably make sure on the exam that it's a bulleted list for you, so it's easy to parse through the information instead of having to read a giant paragraph. But roll an even number, you lose. So 2, 4, so let's say even. And for an even number, the probability would be 2, 4, 6, 8, 10, and 12. So there's 6 even numbers over 12 total possibilities. So that's 6 over 12. And the result, if you roll an even, was that you lose. And since you have paid $2 to enter, the result will be -2. You'd lose $2. Then if you roll a 1, 3, or a 5, roll 1, 3, or 5. And the reason, once again, that I do that, I write roll 1, 3, or 5 is so that I don't get it confused with like 135 or anything like that. So that's 3 different options. 1, 3, or 5, that's 3 different options. So 3 over the 12. And you will win $4, but that's a net positive of $2 because it costs $2 to play. Then roll a 7 or a 9. That's 2 different possibilities. You could either roll the 7 or you could roll the 9. And so that's 2 out of 12. And if you roll a 7 or 9, you win $10. That's a net gain of $8. And then a roll an 11. That's a 1 out of 12 opportunity. And you'd win $18 because it costs $2 to play. Any questions so far?
What if you don't subtract the $2 to play each time? So if you do like you win 4, I think that's how I was gonna.
Excellent question. So that is an excellent question because there are 2 ways that you could think about this. You could think about it as looking at purely your expected value of the game, and then you take off your $2 at the end. And that will work too. And the reason for that is the distributive property of addition or of multiplication over addition. So there are 2, like the reason why it works either way is that you could think of it as 0 minus 2 as your result, plus 4 minus 2 plus 10 minus 2 plus, and then the probabilities of them. And then you could just factor out the -2 at the very, very end. So it works either way. You could either take care of the -2 at the very, very end, or you could take care of it as you go along. Both ways will work. Yeah, of course. Great question. So it doesn't matter if you -2 at the very, very end, or if you take care of it when you're writing your little chart. So the EV, the expected value, is equal to 6 over 12 times -2 plus 3 over 12 times 2 plus 2 over 12 times 8 plus 1 over 12 times 18. If I plug that into my calculator, please take your time on these ones and please write out all the steps, because if you make one false mistake and you didn't write any work, I can't give you any credit because I don't know, like it would take me years to figure out what mistake went wrong, because I'd have to keep trying out. Did you was it a calculation error or was it a typo in your calculator? I don't know which. And to test all the different possibilities would take a long time. So let's do, 6 over 12 times -2 plus 3 over 12 times 2 plus 2 over 12 times 8 plus 1 over 12 times 18. And you get 2.33 repeating, so approximately $2.33 if you round to the nearest cent. So this game is in our favor. This game is in our favor because the expected value is positive. If the expected value was negative, the game would not be in our favor. It would be in the dealer's favor. It would be in the game host's favor. Because if you're going to lose money, they're going to gain money. And I'm not saying that like I haven't, I'm still parsing through my problems to decide which ones I want to do. But just so we're clear, if if there are multi-part questions, answer the multi-parts based on your work. So like, let's say that the question was part A was find the expected value and part B was, is this game in your favor? Answer it based on your work. So if your work said that if you found and the answer was that you got negative 2.33, you would say that the game is not in my favor. And I would give you full credit for that because based on your work, that would be your answer. All right. I don't think we have enough time to do another example, but fair price. Do you guys remember how to do that one? We could probably set one up.
I mean, this one would it just be $2.33?
It would be, I believe so. Well, wait.
So fair price, the same as the EP.
So fair price is done by calculating the gain when you wouldn't pay anything for it. So let's say basically the same thing, except there is no game cost to play. So if we did that, then all of this would change. This would become instead, this would be 0, this would be 4, this would be 10, and this would be 20. And we calculate that. And when we do that, so all the numbers are the same except for the results. We're assuming that the game costs 0 and figuring out the expected value of what you would win. And that would be the fair price. So the fair price is making sure that the expected value would be 0, which is done by assuming that it costs 0 to play, finding out how much you are expected to win each time, and making that the value of the game cost. Is that okay? I'm sorry to do that briefly. We don't have time, but we did do an example of that. There's also examples in the textbook.
Wait, so fair price would be the same B setup, but with just those different numbers?
Yes,
Okay.
and then that would be the fair price.
Don't subtract what you pay to play.
Exactly, because you're trying to figure out what you should pay to play. So if that'll be it for today. If you guys have any questions, please feel free to email me. Otherwise, happy studying, and I'll see you on Thursday for the exam.